All right, welcome. My name is Michael Kolbeck, and today I'm going to be walking you through my implementation of the 8-puzzle AI. Let's first see how it works. So when I run the program, it's going to ask us which of the 3 board puzzles we want to use. Easy, medium, or hard. I'm going to enter easy here. And then it's going to ask which of the search algorithms we want to use to solve that board. I'm going to enter BFS here for breadth first search. And what it's going to do is it's going to print out each of the steps it took to solve that board using this particular algorithm. And then at the bottom, it's going to sort of print out the solution that it found and all the relevant metrics to get there. The number of iterations it took, the depth of the eventual solution, the maximum queue size, the total cost of this solution, and the actual steps it took to get to that final target board position. Let's show this again. This time I'm going to enter medium. I'll try another search algorithm, A2, and we'll do the same thing, just take a little bit longer. A few more iterations, but at the bottom, same deal, prints off the number of iterations, depth, and so on. If we select hard, it's going to look pretty similar, but it's going to take considerably longer, just because this problem does take many, many more iterations to solve. It's going to look like that for most of them, but it's going to bottom out for each one of the algorithms that I implemented. So now that we've seen it, let's take a look at how it works. The way that I implemented a puzzle was through a sort of a class called puzzle, which is an object that stores the state, a particular board state, in a 2-dimensional integer array. Sort of here's the goal, and the starting board state is passed to it as start when it's called from the driver. Now, subclass to this, sort of inheriting all these utility functions, are these individual implementations of the puzzle. Breadth first search puzzle, DFS puzzle, iterative deepening, best first, and so on. And these different child classes actually implement the algorithm itself. The intelligent agent is found in this find solution method, which all of them have implemented, and this is kind of how it works. So each one of these records different board positions in a queue of some kind. For the quote-unquote dumb algorithms, which just follow a pattern, BFS, DFS, iterative deepening, it's stored in a deck, or a two-sided queue, whereas for the smarter algorithms, it's stored in a self-sorting min heap, or a priority queue. It creates this data structure, and then it creates a sort of a starting node, which represents the starting board position, and adds it to that data structure. Now I'll just examine what a node looks like here. A node represents a single board state along with all the information that has to be remembered about it to reach an eventual solution. It's got the board state itself, along with a function called expand node, which is the successor function which is used to then generate its children. When expand node is called by one of these algorithms, so it checks it, sees that it's not the required node, and then calls expand node, what it'll do is it's going to check the board position and see if there are any available moves, up, down, left, right, by moving tiles, and it's going to add that to itself as a linked tree of children here. Those children are then returned and added to whatever data structure is used to store the next board positions in line. So that's kind of how that's implemented. To check for duplicate states, which do drastically increase the amount of running time if it has to repeat over things, I used a hash map here where the duplicate states are stored. Then as it comes back around, so it has already visited, it's called. If it's not already visited, that's when the nodes are actually added to the queue. Now for the more complicated of these algorithms, rather than just sort of going by a pattern, first in, first out, the nodes are sorted by a self-sorting queue or a min heap or a priority queue, and the way that it sorts it will differ from algorithm to algorithm. In the case of best first, it's the number of tiles not on goal, which is a heuristic. For uniform cost, it's the cost of the path. With the various A stars, it's a combination of the two. The heuristic plus the path cost, and then that's compared to a different node to find the correct order. These are then automatically sorted by the min heap and then popped off to return sort of the correct order of finding the correct node. And this has the additional effect of, rather than actually going through this queue and picking out each one of the duplicates instead of adding them, we just sort of rely on this min heap to shunt them to the back, knowing that the optimal board positions or nodes are always going to be selected. For A1, it's the number of tiles not on goal. For A2, it's the Manhattan distances. For my A star 3, I just added together the Manhattan distances and the number of tiles. which just by adding the two heuristics together, it kind of gives them an equal say in the processing, which gives a more nuanced guess as it sort of narrows down on the goal state. Thank you so much for watching. Take care.